So in today's session, we'll start with linear algebra. Okay. I've just given the heading to put these things in the perspective and give you some context. What are we doing and why are we doing it? So as we are on a hunt to understand machine learning, okay, we should be able to understand machine learning, deep learning, and most of these things are somewhat mathematical. I won't say there is pure mathematics involved. Everything is mathematically well grounded. So that's not the case. But here, if you have an understanding of the mathematics, have the understanding of these things, it will make things easier. So in that mathematics portion, what we'll try to cover is, so in this mathematics, we'll cover linear algebra, we'll cover probability, we'll cover statistics, and we'll cover optimizations. These are things we have to primarily cover. But you know, to understand these things, we need some prerequisites, okay, that probably are covered in high school or they're never covered. That's one more problem. Sometimes people are taught mechanical way. So why am I teaching you this algebra myself? I could have just redirected the video series, okay, watch this, and then you would be done with that. So rather than that, what I want you is that you should feel that once you have this intuition of these concepts, okay, because as I usually give the example of tools. So you should have tools in your box and you know what tools to use, okay. Then computation is mechanical, and more or less most of the times you won't be doing computation yourself. If I give you a matrix, I'll tell you find the inverse of this matrix. You won't be doing it by hand. Most of the times you will be doing it by your computer, or maybe you will be using some other tools to compute the inverse of the matrix. But the fundamental concept that you should be knowing is, why do we take inverse? Okay, you should know this why part. Okay, when you know this why part about these tools, then it becomes easy to use, and that's the difference between you and the language models that we are going to have, or maybe the artificial intelligence in general that we are going to have. So there probably they have simulated every intelligence, but now you'll reason with these things. You have these tools in the box, and you know that which tool to use for what problems. Okay, because you have an intuitive understanding of those things. Okay, you have a geometrical notion about those things. So that's the plan. So the plan here is not to just give you mechanical methods, and per se I'll also teach you mechanical methods, how to compute things. We'll do that also. But more than that, what you should focus on is that I just don't want to get into those details till I don't understand the whole thing. I don't understand the whole thing intuitively, and I don't have that picture in the head. Okay, what is it going to do? It's like I'm teaching you hammer, and I should tell you why is hammer required and what is it good for, and what it can do. I cannot just tell you, okay, this is a hammer, pick it and just hammer some nail or something. Okay, then you will probably understand this hammer is only used for nails, but you know that hammer has a lot more functionalities. That's what this algebra, or that's what the concepts that we'll teach, they have much more functionalities, much more applications in the real world, okay, that we're going to study. So my basic thing is, you should get the intuition. Okay, you should think in those terms. You should think in terms of mathematics. Okay, when you see something, your worldview should be now somehow shifted. Your perspective should be such that when you're looking at a thing, you should look as if you are having a mathematical problem, and then you're trying to model it mathematically. Okay, that is what will make you a good mathematician, and in turn, it will make you a good computer scientist, because computer science is just a tool. Okay, so is the maths, and you use it to solve the real world problem. So this is the notion. Don't just have this. Okay, so this is required, those mathematical computation. We'll be also learning this. It's not that we'll not be learning this. So in the course of these things, we'll be learning this mathematical computation, and we'll learn the mechanical methods. But you should know the intuition behind it. You should understand it. Why does it happen so? Okay, let's take an example. Let's suppose you know how to perform matrix multiplication. If I give you two matrices, and I'll tell you, okay, perform the matrix multiplication. I think most of you, 99% of the people, will be able to perform matrix multiplication. But if I tell them, why is it done the way it is done, and I think the percentage will drop down to 10-20%. Okay, and after going through these things, so I should be at least confident from my side that you people have got intuition about these tools, and you know why part of the tools, and now you have the tools in the toolbox by which you can use them, and you can reason, and you can use them anywhere, whether you are in physics, then you are in machine learning, you are in mathematics, whichever field it is. And then when you have tools and you have the right intuition, and after that it becomes easy to use them. So this is the notion of math. So we'll again we'll sort of study it from a rediscovery point of view. By rediscovery, I mean you should be able to discover these concepts yourself. Usually I tell this example to many people. Probably these Newton, Einstein, they have an advantage over us because they were born before us. Okay, probably if we were born at that time and we have faced the same problems, we could have invented the same tools if we use the same right logic. Okay, so we should see these things from the rediscovery point of view. Now let's go to the linear algebra. So before understand linear algebra, we'll start with vectors. Okay, this is what we will start with. So we'll start with the vectors. So as you know, this linear algebra, just a side note, this linear algebra is a branch of mathematics usually focused on what's called as vector spaces and linear mappings between them. And the fundamental problem of linear algebra is basically you have these equations and then you find a solution of some sort. Okay, and I know many of these things went over your head, but it's all right. After you watch this lecture again, you should be able to understand the definition. So core concept is what is a vector. Okay, if you ask me what is a vector, so now there are three answers to this question. What is a vector and why do we require this essence of the vector? Why do we need it? Why do we need the concept? Okay, let's suppose if I'm a physicist, okay, if I'm a physicist, I'll think from three perspectives. We'll think from three different perspectives. Okay, usually because these are the three types of people which usually use these vectors. Okay, we'll ask a physicist. Spellings can be here and there, pardon me for that. And then there can be computer science people. And then there can be mathematicians. Okay, so if you ask a physicist, let's suppose what do you do in physics, so they'll answer you probably, we deal with physical quantities. Okay, what are these physical quantities? So physical quantities are something that I can measure, and he'll probably give an example of force. Okay, he'll probably give an example of velocity. Okay, he'll give you lots of examples. He'll tell you I deal with these quantities which are there in the physical world. Let's suppose you have a body and some force is applied. You are in a car is running with some velocity. Okay, then he'll tell you, okay, when I am dealing with these physical quantities, force, velocity, I see a little bit difference in them. Some quantities are quantities in which if I just give you information about the number, if I just give you a numeric value, that's more than enough to describe it. Let's suppose I can give you for the force, let's suppose I'll give you 50 Newton. This is more than enough to sort of tell you the value of this. But there are some quantities for which it is not enough you can give a numerical number. For that you should also give the direction. Okay, so direction in which basically that thing is happening. For the velocity is one case, displacement is one case. Okay, from physics perspective, if you ask them, okay, now you have these quantities, physical quantities, now you have these two types of quantities. So one quantities are the quantities in which one number is just enough. If you give me the magnitude of that thing, if you give me a numeric value for that, let's suppose time. If I give you a number for time, let's suppose I'll give you 10 a.m. This is the number. Okay, this is basically a magnitude. So this is enough to describe this quantity of time. But there are some quantities, as I said, velocity. Okay, you should give me velocity is basically speed plus direction. So you should give me, because sometimes you ask somebody, oh, where are you going? So he'll tell you I am going with this speed in this direction. So basically he's telling you the velocity. So now one thing is not enough. In some quantities, one thing is not enough to describe it. So here you need extra thing. So one thing is magnitude, maybe let's suppose 10 meters per second, and then plus you need a direction for that. So what you say is towards north. So towards north or something. So if you see these sort of tools, so then we had to come up with the mathematics. So physicists saw, okay, what is the math? Is there some mathematical construct that somehow I can divide my quantities in this? So then they found that, okay, yes, we have. So we can have physical quantities, we can divide them into two things. So one thing can be scalar quantities, where I just need one single number to describe them in their entirety. Let's suppose time is there, and things like other things which you can represent, distance is there. Okay, and these things are the things which only require a magnitude, which only require a scalar number. A number basically is called scalar. Okay, we just require a number to describe them in their entirety. But then there are quantities, okay, which by quantity I mean which we can measure. For their measurement or in order to describe them, this giving magnitude is not enough. In order to give additionally you should give the direction also. So first you should give magnitude, you should give direction. Okay, for that, so physicists will tell you a vector is that which has magnitude as well as direction. But this comes whole from their perspective, okay, because he works on the physical quantities by which he can measure. And now you can see that quantities are of two types, scalars and vector quantities. Or maybe physical are those which are only represented by the magnitude, and vector quantities are those which are represented with the magnitude and they have a direction also. Then let's go to computer science people. Okay, if you ask me, okay, to you, what are numbers? I say numbers are nothing. If I write something like this, if I write 2, 4, 6, 8, these are a bunch of numbers for me, and if I club them together, this is a vector for me. You tell me, okay, why have you discovered this concept? Why do you need this concept at all? I can tell you, okay, take an example of an image. I'll tell you, take an example of image. Okay, this is an image, because let's suppose we are computer vision people. Okay, we deal with computer vision. So I'm saying this is a picture. So you know each picture is made up of pixels. Let's suppose this is a picture made up of 28 cross 28 pixels. So in total we have 784 pixels. So each of this has a value. Each pixel has a value, because at the end of the day, picture is nothing but numbers in computer. So in computers we store everything with numbers. So here we have a number. Let's, for the simplicity, this is a grayscale image. So there is just zeros and ones. So 0 means it's white and 1 means it's black. Okay, so these are two numbers that can be here in this cells. So you know, if I flatten this out, so in total I can represent this image with 784 numbers. So this image can be represented with 784 numbers. So I can just write these numbers like this, 1, 2 until 784 numbers, whatever numbers, because these numbers are not binary, they can be zeros and ones. So this is one concept where I have to use these concepts. I'll say this is a vector. So other thing is, let's say if you are from graphics or visualization design, so there you see things moving on the screen. So what you basically are doing is, the actual screen is nothing but pixels. You have to move these pixels here and there. Okay, so if let's suppose if this one was here, so initially let's say we had a picture of man like this. Okay, these are just pictures, these are just images made of pixels. Now if you want to make him dance, the point is that what he'll do is, he'll probably just move his body in different directions. Okay, this is the direction he'll move in the body. So what computers are doing is, they are doing some transformations. They're just taking these pixels, moving them here and there. Okay, and this thing also requires, so initially there were a bunch of numbers. So initially it was a bunch of numbers, this was a bunch of numbers. So after in the second frame, let's suppose this again was a bunch of numbers. Okay, but the numbers here and numbers here are different, because now these two pictures became different. So what happened in between? What happened in between is called transformation. So you took a vector and you did something onto this and it transformed, and here it was static and now you see the person dancing. So in between you did something, that's called transformation. You transformed the things, and for these things I need vectors. So from a computer science perspective, what are these vectors? They're just array of numbers. Okay, you have an array of numbers. Okay, this is what vectors are. So as you know, the mathematicians have the tendency to make things general. So what they did is, they combined everything. They said, okay, physicists look vectors like this, computer science people look vectors like this. So let's do one thing. Let's combine both of these approaches and come up with a generic approach. So what they said is, they said we'll define what's called as vector spaces. Okay, so they defined vector spaces and said they have some fundamental properties. A vector is an element of this vector space. So vector belongs to this vector space. So we'll come on all these definitions, what a vector space is, and what does it mean to belong into a vector space. Okay, so from mathematics perspective, what they did is, they said we'll combine both of these things. As these things have some property, these things have some property, let's put them into a realm, let's put them into a framework, into a template. So what we can do is, we'll define something called as a vector space. Okay, vector space will have elements. So one element of that vector space, we'll call that a vector. Okay, these are the three perspectives. If you see from the people, if you ask them what vectors are, they'll give you these three perspectives. Okay, and the most mightiest perspective is of the mathematician. Okay, because they engulf everything in that. And here, more than computer science people, now we'll look it from the we'll look it from the mathematics perspective, and but we'll see it from the mathematics perspective, but we'll apply it in computer science. Any questions till this? Any questions? Just for the sake of completion, what I'll do is, as we got a question, if we see maths, and then we have to see its applications. Okay, that's also a motivation. So for that, what I'll tell you why linear algebra is used. Just for the sake of completion, you don't need to know them, but you should at least have an idea. So why linear algebra? Okay, because we are computer science people, more or less most of us are computer science people. So we'll see why this application, why are these applications of these linear algebra. The first thing is, which we are going to study for quite a long time, is machine learning and data science. Okay, AI, machine learning, deep learning, wherever you see it. Okay, this is the first thing where you will heavily use it. And then other application is computer graphics. Okay, computer graphics people use it here and there, right, left, everywhere. Okay, then physics and engineering. Physics and engineering people. Okay, because now why I'm talking to physics, because sometimes you do simulations based on physics, so there you have to do these matrix manipulations. Okay, and then as I said, optimizations again, this, if you see machine learning and deep learning, this is just some way of stats and optimization. Okay, there you use this linear algebra a lot. Okay, and these graph theories, if you have heard of graph theories, so graph theory is a subject where you study about these graphs. So there are a lot of things in graphs which can be represented by these basically by numbers, and machines just do, they crunch these numbers. And then cryptography. Okay, you can use this in cryptography, you can use this in quantum computing. Okay, and network analysis, and we can go on and on. There are a lot of things which use this concept that mathematician has developed, that's called as linear algebra, and these are some of the applications, and you can find a lot of applications, a lot more applications. So this is the answer to the question that was asked: if we found maths, okay, how to apply it. So see what are the applications. If you have maths, okay, where is it applied? And there are a lot of resources that can give you that. Or if you are sort of seeing the math and then you are not able to probably find the applications, then it's a topic of research. Okay, where is this maths useful now? As I usually say in number theories are discovered, and people thought probably it won't have any applications in real world, but the whole cryptography was based on number theory then. Okay, so these are some of the applications. Like there are a lot more, I just named a few so that people know where are we going to do this. Now let's deal with it. Okay, let's take it one by one, chunk by chunk, so we understand it from a rediscovery point of view. Okay, I'll start with the stories. Okay, as usual, because we're living in real world, and I don't want you to differentiate between real world and academic world. If you are doing something, and if you are not using it in your day-to-day life, then it is somewhat a waste. I won't call it a full waste, but it is somewhat a waste. Okay, let's start with the story. Most of us are probably responsible people in our families. Let's suppose you have a small brother. Okay, this is probably one of you, and this is your small brother. Okay, I'm a computer science major, not an art major, so my art is terrible. So this is you, and this is your brother. Now what happened is, someday what happened, your brother came out of his home and he went somewhere wandering. Then what you are doing is you're asking people, where did he went, where did he went. Okay, so basically what are you asking to the people? You're asking to the people the position of your brother. Okay, so where is he located, where is he located? So you're asking people. Now people can give you different types of answers. Okay, so they can tell you go there, go here, they can give you direction, proper directions. Go straight from this point, go straight these meters, then go right, then go left. Okay, so because they have these directions, so they'll give you directions in different formats. Okay, so this is what you want. You basically want his position. So you have a brother, you want his position. So one way of doing that is, so people can tell you, if you are at this point, go straight, let's suppose some 1 kilometer, then go left. Okay, then again go straight, then turn at 30-degree angle something, and you will find your brother like this. This is one way telling you a position of an object. Okay, and other ways can be, let's suppose they can tell you your brother, let's say your home is right here and your brother is somewhat here. So what they can say if you draw a horizontal line from your home, okay, and then if you go by, let's suppose, 30-degree angle, and if you walk straight, and you will find your brother, and assuming that there is no house and this is a plain area. So what I want to convey is basically there are different ways to define position. So one is this method, one is this method, and there are lots of methods, and you guys can come up with your own methods. How do we define position? Okay, in a mathematical sense, if I have to then mathematically tell it. So what I can say, this is something called as polar coordinate system, and this is something called as Cartesian coordinate system. Okay, so I just gave you an example. So this is called as Cartesian coordinate system, and this is called as polar coordinate system. Okay, you can come up with your own systems, because the problem is that you want to find a position of a thing. So if you see how you solve this problem, so you solve this problem by first fixing a thing. Okay, this is sometimes called as origin. Okay, or maybe a frame of reference from which where you are looking. Okay, I'm starting from this. You are defining that origin, or you are defining that reference point. Okay, from which you are going to basically see the world, your perspective, you are that eye. So let's suppose you have a camera over here, you stayed there. So you define origin, and after that you told, okay, you can go straight, then go left, go straight, go left. Okay, so this one system that I named is Cartesian coordinate system, and the other system I named is called as polar coordinate system. Now before going to this, okay, can I tell something about this location now? How can I describe this? Okay, this is basically a point. If you see this as this is a point. So position is nothing but a point. If you see it, mathematically I can call it a point. So how can I define a point now? Okay, so as I said that you have to define a reference. So a point usually is a location. Okay, it occupies no space, it has no size. Okay, and it has some dimension and shape. So you can say let's suppose two numbers are enough to represent a point. So for position we need a mathematical construct. So what mathematicians do is they'll take this problem, they'll say okay, we don't want to solve this problem only, we'll solve all the problems that follow in this template. So what we do is we'll call instead of position we'll call it a point. Okay, it can be a position, it can be something else, but how can we abstract these details out? So as I said, the first fundamental of mathematics is this: they'll see some problem, okay, and they'll see a pattern in the problem, and they'll find a bunch of problems like this. They'll see a lot of problems like, and which follow this template. So what mathematicians do is they say, oh, we'll club all of this together and we'll build some mathematics on this. So as was with the functions, I taught you functions. So in the function, the template was that if some quantity is somewhat interrelated to other quantity, if they have an effect on each other. So that was, and there are humongous number of problems of this sort. Okay. Similarly, if you see this position, you are required to find these sort of things everywhere in physics, in engineering, mathematics, and probably in computer science. So what mathematicians did is they said, okay, we'll abstract out all these details. We are not caring about I just want to find position. Okay, what I'll do is I'll define some abstract notions. I'll define a point first. Okay, I'll define the point. So how I'll define the point? So what I said is this is just like position. You can come up with your own system. So you can say my home is like origin because I start from there, and after that I can define it in certain ways. So the first thing that we studied is we just saw that is Cartesian coordinate system. Cartesian coordinate system. So what mathematicians did is they said, okay, let's suppose we are in a 2D surface, okay, because we'll deal with because this point. Let's suppose we'll take this 2D. We'll take this 2D Cartesian plane. It can be 3D also. It can be 4D also. So we can imagine in 1D, 2D. Let's take it the example of 2D. 1D will just be a line, and 3D will be in 3 dimensions. We'll take the case of 2D, and then we can extrapolate it to wherever you want. So in if you are living in 2D, let's suppose if there's a plane surface, what you can do is you can just draw these two lines. One line like this, which are orthogonal to each other, which are perpendicular to each other, which make an angle of 90 degrees. So what I can say is this point here is origin. Okay, this point here is origin, and I can say the value of this point is 0, 0. This is my reference. 0 basically means nothing. I have not initialized anything. So what I'm saying is, if you now give me any point, let's suppose you give me this point P, I'll call this P. So now if I have to describe it, so what I did is I first established a system. I said, okay, what I did is I divided my space like this. I kept a reference like this, and you saw these two straight lines. So what I'll do is now to reach this P, if you see, I have to go like this. I can go like this till this point. Okay, till this point on this axis. Okay, and I can go then vertically to this. And so any point, if you give me any point of space, this was point P1. If you give me some point P2 here, so I can have these two things. I just have to walk two distances, one in horizontal direction and one vertical direction. Let's suppose this P2. If I have to reach this P2, so what I'll do is I'll start from origin, go here till this point, and then I'll go vertically. So only two motions are required now. I have to require a horizontal motion, and then I require a vertical motion. So don't you think that each of these points can be reached this way? Okay. So if each of these points can be reached this way, so we define this as a system. Why is this? Because it's complete. We can reach any point. And now let's suppose from this 0, if you are walking towards the right and you walked some 3 kilometers, and then you have to go vertically, and you went vertically some 3.5 kilometers. So you can call this point P1 3, 3.5. You represent it by two numbers. Okay, you represent this point P1 by using two numbers. That's 3 and 3.5. So 3 basically tells you if you start from the origin. So you have to walk in the right direction. You have to walk in this right direction 3 units, whatever the unit can be kilometers, meters, centimeters, whatever it is. And then if you stop there and then you go vertically, you have to go 3.5 units upwards, and then you will reach this point. Is it clear for everyone? And we call these things as axes. So we call them axes, and this is called as x-axis, and this is called as y-axis. Okay, and here we call this point as origin. This is one of the systems by which we can define point, by which we can show the position of the point. If there is a point, I can just choose an origin, and after that I can reach anywhere. Okay. Second system can be I have what's called as polar coordinates, which I showed. Again, that will be somewhat similar. So we'll have again these axes, But here, this is the origin. So now if I have a point P here, let's suppose I have a point P here. So what you basically do is, so for this point, you draw a straight line, you just see the magnitude. Okay, you see the direct, what is basically the distance between this OP. Let's call this R, and then you see the angle theta. So this point P can be represented by R comma theta. Okay, any point, let's call now, let's have this point somewhere else. Okay, and if you draw a line like this can be R2 and this can be theta 2. Something like this usually. Oh, sorry. So we measure theta with the axis, we can call this as theta 2. So here R2 is represented by this point, let's call this P2. This P2 is represented by R2 comma theta. This is another system which is called as polar coordinate system, and more or less we'll be concerned with this system called Cartesian coordinate system. Okay, and then you can basically interchange these systems each other. So you can, if you have polar coordinates, you can change them into these Cartesian coordinates. If you have Cartesian coordinates, you can change them into polar coordinates, and that is left as an exercise, and see how we can convert. Exercise is that you need to know how to convert one system from other system, and it's really easy to convert. Okay, and then there are other systems. There are systems which is called a cylindrical coordinate system. There are systems which are called spherical coordinate systems, and there are a lot more concepts than these. Okay, so now the point is that now we learned something. We learned that we can describe a point. Okay, we can describe a point with these two numbers. Now this is in 2D coordinate system. So how is a 1D scalar then represented? Then we'll have just a line. Okay, if the universe is 1D, so here this is my origin 0. Okay, then I'll have 1, 2 something distance like this. If something falls on this, I'll have negative values on here. Similarly, if I have along the y direction a scalar, so I'll have 0 over here, I'll have positive numbers over here, and I'll have negative numbers over here. This is my positive numbers. If you see this 2D coordinate, it has divided the whole space into 4 quadrants. This is called as first quadrant, this is called as second quadrant, this is third quadrant, and this is my fourth quadrant. This is how it has divided the things. Okay, so far what we have done is we have just defined a point. We have seen how to define a point. So now if you see this point, so from a computer science perspective, this point is represented by two numbers. If you have a point in 2D plane, let's suppose, so that point is represented by two numbers. So that is x1 comma y1. So what is the value of x and what is the value of y? So here you can call it a vector. So see how mathematicians beautifully call it a vector. So if for a physics person it was a position, let's suppose for a computer science person it was a pixel. So what we did is, so we had to have some frame of reference. So we said, okay, now let's define the Cartesian plane, and for that we'll have two numbers to describe it. Because if you see your screen is 2D. It's pure 2D. Okay, because it does not have that. It has length and breadth. It does not have the width. It's 2D. So for that, if you have to describe any pixel, you can give me two numbers. So as we did with the positions, I just told you the example from a physical thing where you are finding your brother and you had to locate his position. Okay, then we came up with these Cartesian coordinate system. Is it clear for everyone? Is it clear for everyone?
Yes.
Okay.
This position system can be related to that our any Uber apps, like where we can find out our outside.
Yeah, and there we represent these things as graphs. Then there, okay, all these graphs and they represented by these matrices. Whatever we are going, they are basically numbers. Okay, so that is the system. So what I want to the point I want to go get through is, so if we have a problem, we have to come up with the mathematical construct. We had a problem, okay, how to define position. So what we came up with, we said, okay, we have to define origin, and after that origin, we have to define the things in a certain way, so that each point is uniquely represented. So if you see this point and this point, these 2 points are quite different. Okay, now if you made a system where these points are shown the same locations, then that system is somewhat rigged. It's not a good system. So you should come with the system, these 2 points should be represented differently. So they should have different representations. Okay, and if 2 points are closer, let's suppose this and this, the 2 points, the values should somewhat be closer. And if 2 points are farther, the values that you are going to these points, it should be somewhat farther. So these are notions that while you are solving a problem, and you have to keep them in the head. Okay, any other questions? Mahmoud has some question. Yes.
I would like to know a little bit about complex numbers here, because these numbers will be like integers only. But is the coordinate system somewhat same for the complex numbers? And
So
could you just
that's
describe?
representation. Whatever you have seen in complex, that's a representation. So we'll have to take a different probably lecture on complex numbers, but that is just how we represent those numbers. And these numbers appear in real world, and then we said what to do, because we have a component which we can explain. So we said, okay, let's have let's call it imaginary components, and they're called imaginary numbers, but they are not imaginary. They exist in real world. These complex numbers, they exist in real world, and these numbers are nothing but representations. If you say me what is 3, 3 is nothing but a representation of some quantity. If I can say you I have 3 pens, okay, in a similar way there are some quantities where we require these complex numbers. Okay, these complex numbers are required because they describe some physical quantities, and maybe not our daily quantities which we use, but the quantities that we deal probably in physics. Okay, they require the complex numbers. Think maths like this. Mathematics is just an explanation of what is going in the world. Okay, what is happening in a phenomenon. So if you have these number system developed, so why did you develop it? You developed the system because you wanted to quantify the things. Okay, usually I ask this question: if you were living in where people were nomads, you had no civilization, and if you have to tell your friend there are 3 lines and they are very hungry, ready to eat, you don't go there. How will you tell you? How will you tell him? You have to come with a system. You have to show, oh, there are three lines like this. This is unary system. Okay, because you are showing 3 fingers. Just these 3 fingers are nothing but just representations. And these numbers, if you take the numerical value, we have 0, 1, 2, 3, 4. 1.2, 5.2, something like this. These are the numbers that we use in our real quantities, real world quantities. Okay. Then we came up with complex numbers because they were required in some quantities. They were required once we were explaining some physical phenomenon, and we said, okay, let's come up with these numbers, which is called as complex numbers. And we said, okay, now they also have 2 components. They have a real part and an imaginary part. So see this point. This point basically again it requires 2 numbers to represent it. It requires 2 numbers, that is, both of them are real numbers. But when you represent quantities which require the concept of these complex numbers, so there we say that it also has 2 components now. It has a real component and an imaginary component. I hope I got the point through. Mahmood?
Yes, yes, I think for now it's good.
Yes, and we can have discussions on complex numbers like separately. Where are they used? Why are they? So we can have the discussion. But here you should think about the maths in this direction.
Mm.
Okay. Now if you see this, you can draw these points. So here again I have a point like this. I'll be now working with more or less 2D, and we'll also imagine 3D. So this was my 1D. So this was my 1D case, and this was my 2D case. And now what 3D does is I'll make 3 orthogonal lines. So I'll have now 3 lines which will be orthogonal to each other. By orthogonality I mean they'll be perpendicular to each other. They'll make a 90-degree angle to each other. And there, if you have a point P like this, so okay, so it will be represented by 3 numbers now: x1, y1, and z1. Okay, and we call these 3 axes as x-axis, y-axis, and z-axis. Again, this is a coordinate system. So one coordinate system is 1D, then 2D, and then 3D. And we'll be more or less dealing with this. We won't be dealing with the polar coordinate systems much. Okay, but they might be required sometime. But for that reason, I just introduced them, and if they are required, I will explain them that time. Now this is our vector, and if let's suppose I have a point over here. So I have a point. That's my point 1. Okay, so from a computer science perspective, this point is just a number, bunch of numbers. So for me, it's like, let's suppose 3, 4, 4. For a physics student, what this point is P, this is like a vector like this. So he'll draw something like this. He'll say this is a vector and it has this magnitude R, and this is the direction. He'll give direction as well as the magnitude. Okay, for computer science person, this showing this much is enough. Okay, but now what we are trying to do is we are basically trying to generalize the concept. Okay, you got the concept. Now we have the point P, and now we have developed a system. Now we will understand the related concepts. We'll see what can be done with this point. Okay, so what can be done with this system if we have now developed a system. So there has to be tools so that we can manipulate these things. We can do something with the system. I said that this point can be moved from here to here. Okay, but how much to move it? Okay, if I have to move this point from here to here, let's suppose in computer science. So how much to move it? Okay, that's the question now. So for that, we now should have some notion of telling you the distance between these points. So distance. The first we'll see distance of points from the origin. From the origin. Okay, so what is the distance of these points from the origin? So if you have a Cartesian plane like this, and if you give me a point P, okay, what is the distance if this is origin? So what is the distance of the origin from the origin? Okay, if this is in 2D, and this can be in 1D also, this can be in 3D also. So you have to come up with the formulations, the mathematical formulations, okay, by which you can find the distance of the points from the origin. So if this is a point, so I'm taking example of 1D first. So 1D point is easy. So let's suppose if this is 1D line, and here we have the 0, and let's suppose some point is represented here. Okay, so what we can do is we can just see how many units it's away from here. So if it's, let's say, 4, so we'll say 4 minus 0. So the magnitude will be 4. So we'll say it is at the distance of 4 from the origin. And the question becomes tricky once you have this. Okay, once you have this thing. So you have this point P, and it has some value. Let's suppose x1, y1. This is the value. If this is the value and we have to compute the distance, so basically we have to compute this. This is what we have to compute. Okay, so what I can do is I can use Pythagoras theorem, because what I can do, I'll draw a perpendicular from here, and I'll say I know this distance from there here to here, it's x1 by definition, and from here to here this is y1 by definition. Now if I want to so find this distance, let's call this d. So this d square is equal to x1 square plus y1 square. Okay, and I can say d is equal to under root of x1 plus y1 square. Okay, so this is the distance, the point from the origin. If you give me a point x comma y, this is the distance. And similarly I can do it in the 3D. So 3D will be 3 dimensions, and I can use the Pythagoras theorem repeatedly there, and I'll come up with this formulation. So basically now if you have an ND point, so see the beauty of maths. So here you are able to visualize 1D, 2D and 3D. After that we are done with visualization. We cannot visualize, there can be a point which can have 4 dimensions, which might require 4 numbers to represent. So we are okay. If a point lies in 2D, two numbers are used to represent it, and x-axis and y-axis. If it lies in 1D, one number is enough to represent it. Now we have also notion of 3D. If a point lies in, let's suppose, in air, okay, I can say it is in 3D because our space is 3D. But we have no notion of 4D. We have no notion of 5D, ND. But maths does not care about it. Maths will deal with everything. So it will say, let's deal the ND case. So we'll say if we have ND, ND basically means anything that quantity requires now n numbers to represent. Okay, so here n numbers can, let's call this point P, and we can be calling it a point. So P, it can be, let's suppose, x1, x2, x3 and so on till xn. So these are the dimensions that thing might have. Okay, so because that physical quantity might require n numbers to represent it. Let's suppose an image. Okay, an image, if it is an image like this, as I said, 28 cross 28, it requires 784 numbers to represent the image. So that means this image lies in 784 dimensional space, not just the 2D. You are seeing the 2D because it has the length and the width, but if you see it from pixels, so this image lies in 784 dimensional space. Okay, so that's the number. So we require 784 numbers to represent. Now we have to find the distance of this point from the origin, so that we can clearly extrapolate this. Okay, so what we can say is, we can say d is equal to under root of summation of xi square. I goes from 1 to n. Okay, and you can just verify the formula by induction. You can use mathematical induction to prove it. So the first thing that we studied, we said, okay, we had a point. So now we have to compute the distance of this point from the origin. So what we did is, we used some mathematical tools. We came up with a Pythagoras theorem, and we said, okay, we had this d, we had this x1, we had this y1, we used Pythagoras theorem. Now I'll show you one more thing of the maths. So maths is that it converts the point. I told you about polar coordinates also. I said there can be polar coordinates like this. Okay, this may be the point P that we had, and this is my, let's suppose we call this D. And let's suppose this is theta. So this point P is represented by D comma theta. Okay, that's the representation of this point P. So can I come up with this? Okay, what can I say about D? Can I derive it from mathematics? Can I derive it from there? So what I can do is, okay, let's call this number. So I'll draw a perpendicular from here, and this line over here till this line, and this line, let's suppose. Okay, so if you say in trigonometry, what can you say about this? So if you see, sine theta is equal to, this is my perpendicular and this is my base. Let's call this B base, let's call this hypotenuse, let's call this perpendicular, and this is my hypotenuse. This D is my hypotenuse. Sine theta is equal to perpendicular by hypotenuse. So hypotenuse is D. Okay, so what I can say about this P, so this P is equal to D sine theta. Okay, this P over here, the value of this is D sine theta. And similarly, you can say that the value of this B is D cos theta. Okay, this is the value. So let's call this, now this is the value of X and this is the value of Y. Okay, so now what I'm telling is I have to compute the value of this D. So what I can say is, see the mathematical tricks now. So I can square both of these things and add them together. I can say x square plus y square. So I'm squaring this and adding them together. So that's equal to D sine theta whole square plus D cos theta whole square. Okay, so if you see this, so this is D square sine square theta plus cos square theta. So this is equal to D square 1. This is x square plus y square. So now if you see this, D is equal to under root of x square plus y square. We again landed the same answer. The first thing is we solved the thing with the Cartesian coordinate system. We had the Cartesian coordinate system like this. Okay, and the Cartesian coordinate system was like here. So we said we can apply Pythagoras theorem. So this is a right angle triangle, the right angle is here, so we can say hypotenuse square d square is equal base square plus perpendicular square, and then we took a root. So I said there is another system that you can use, that I said polar coordinate system, in which we represent things by two numbers, that is this d and theta. So what I did is I told you this distance is basically d cos theta, and this distance over here, this is d sine theta. So now I have to compute d. So what it is, I squared them and add them together, and I'll end up with the same formulation of the distance. Is it clear? So see the beauty of maths here. So sometimes numbers tell you something. If you do the mechanical way, so numbers tell you something. So there are different ways to arrive at the answer, and they tell you the different stories. Okay, and maybe the underlying concept is similar. So here the underlying concept was we were basically measuring the distance of this p from the origin, and but we had two different systems, and both of these systems gave us the same answer. Okay, and they told us, okay, this is the distance from this system. Is it clear so far? I'm pausing here for a second or so that I can take questions. So the question here is, if you see that this image is basically seen as 2D thing. Okay, so if you see the generic usage of this term 2D, so how do we use this 2D? So anything that is represented by only two, if this is an image, okay, if this is an image. So the definition boils down to how you represent the thing. So in day-to-day life, you say image is a 2D. This image is a, let's suppose, 2D surface, or it's a 2D plane. So why do we call it so? Because you know that image just has length and it has a breadth. It does not have a thickness. So if you have to tell something about the image, what you can tell? I took a photograph, and the photograph was this of this size. It was, let's suppose, some 1280 cross 720. This was the height and this was the width. Okay, and this is 2D because only two numbers were required to mention its size, and this was something to deal with size. Now see. Now when you talk about image, if you have processed the image, you are not talking about size. You are talking about the pixels now. You are saying, okay, this is the image. But you know that I am not concerned about the size now. I am concerned about the pixels it has. So if it is 20 cross by 20 cross image, so each of this, let's suppose a column or a row contains 28 pixels. So I need 784 numbers represented. So in that perspective, this image is 784 dimensional. Okay. So dimensions basically tell you how many numbers are required to represent this thing. So here if you tell me, okay, what is the size of an image? I can say you in size, this is a 2D thing. Okay, in size, if you talk about image, then image is a 2D thing. Okay, but in pixels if you say, then it is a 784 dimensional thing in this case. Okay, it depends on the question that you ask. If you ask me, okay, what is the size of image? Then I'll say you by according to size, image is a 2D image because I only need two things to represent it. But if you reverse the question, if you say me, okay, there are so many pixels that are there in the image, then how many numbers are required to represent an image? So there are 784 numbers if image is of 28 cross 28 pixels. Okay, now because I'm not talking about size now, I'm talking about something else. I'm talking about the information that there is. Okay, so that's the difference between the questions. So dimension is related to how many numbers do you basically require to represent this. So in size you require two numbers, but in information you require 784 numbers. And sometimes when you talk in real world, you say image is 2D. Why? Because it has length and it has width, or maybe it has length and it has breadth. But when you talk about in computer science, you say it is it is n dimensional. Why? Because we need n pixels. So n can be 784, or it can be the number of pixels that are in the image. So is it clear?
I would say partially.
Okay,
And
but can you ask me like why it is not clear? I can give you the more
yes,
sophisticated answer
so
probably.
then there is one more dimension, like the I would say that in multispectral images,
Yes,
we
yes, yes,
have,
yes, yes,
yeah,
yes,
we have like 90 more dimensions.
yes.
So how would that relate to that?
That's why these dimensions are. Sometimes you write. I just took an example of this. I said this image, this R belongs. This image, let's suppose it belongs to. Every value is a real value, and it belongs to 28 cross 28 dimensions. So sometimes if you have multiple channels of the image, because now you have RGB colors, so now the image is not, each pixel value is basically represented by three numbers itself. Okay, and this image is now 28 cross 28 cross 3. Okay, because 28 pixels and each pixel is represented by 3. So you can say this image now belongs to, so which takes real values 20 cross 3. So this many dimensions are required. Okay, so these many numbers are required because each pixel is now it requires 3 numbers. So now I have these many pixels and multiplied by 3. These numbers are required to represent this image. Information. When I'm talking about information, I'm not talking about size. Okay, there's a difference between question. Difference is if I just ask you the size, then according to size, image is 2D. Okay, because why is it 2D? Because we are talking about length, breadth, and height. So length, breadth, and height. If you talk about size, So then things are categorized differently. 2D basically means which have two other dimensions, length or breadth. Okay, 2D shadow, a shadow is 2D. Okay, is 2D because why? Because you need only two numbers, you need length and breadth. Okay, you are done with the numbers, you are saying this is a 2D surface. Okay, but if you are now saying me about the information, for the information I'll have to change, I'll have to accordingly see how much numbers are basically used, are maybe are required to represent that thing. So that's the question about dimensions, how many numbers are required. Okay, and the question is, are you talking about information or are you talking about the size? If size, then probably image is 2D. Are you talking about information, then the dimensions change. Is it clear now?
Yes, I think it's clear, and I would like to ask one additional
Yes,
question.
yes,
Maybe,
yes.
so how would we quantify the dimensions, number of dimensions? So, do they need to be orthogonal all the way, or all the times? And this is one part of the question.
No, 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 no. Neha, good question. We'll come to that because now you're digging deeper into the questions. These were the questions asked by mathematicians. Okay. Now what are these dimensions? Now what are these dimensions? It is necessary that they should be orthogonal? No. So I'll give you an answer here. The answer is that these dimensions they should span the whole vector space. They should span the vector space. And now what is the vector space? What is the span of the what is the span vector space? We'll answer this. Okay, just now take this as an answer. So I am saying you the dimensions basically, and these are called bases. Okay, so what you talked about is called bases. So should they be orthogonal? So bases need not to be orthogonal. So bases are the vectors which span the vector space. And what are these concepts? We'll come to that. But this is the actual answer to your question. So you're saying that whatever numbers we represent, so should these things be orthogonal to each other? It's not necessary. We can have non-orthogonal bases also. So bases basically mean which span the vector space. Okay, and hold on your horses. This is a big hash and big question mark, and we'll see what this is slowly when we reach these concepts. But it's a good question, so that you had these questions. Okay, how to represent this now? That's why people came with the concept of basis. Okay, you might have heard. Okay, now we have this 2D. We have this 2D. We call this I cap and we call this J cap, and we say these are standard bases. These are standard bases. Okay, this I cap and J cap or I hat and J hat, they are standard bases. They are unit vectors. So what basis means? If you give me any point, let's suppose P. Now this P can be represented in these basis vectors. So if this number is 3, 4, so in basis I can represent it by like this: 3 I cap plus 4 J cap. So what I mean by span basically is you should choose those sort of bases with the help of which you can, if you choose any type of point, any type of vector, these are vectors now. Okay, and the whole thing is a vector space. Okay, now this I and J cap is the basis of the vector space, and it should be such that it spans the whole vector. What does the meaning of span? Each vector should be represented by these bases. If they are not if the things are not able to represent it by these, they are not called bases. So basis vectors are so special vectors. So you can just take some combination of these vectors and you can make any vector from this. So this whole thing is now a vector space. Okay, and this I and this J, these are called as basis vectors. Okay, why are they called base vectors? Because you can reach any points, you can represent any point by just using these two things, by just doing this I cap and J cap. But more details coming. Okay, because otherwise people will we're going ahead of time. We're going basically ahead of our lecture. That's good because these questions should be naturally coming. Fair enough now. At least understood some parts.
Yes, nice. Thank you very much. And one more additional question, maybe with that. Maybe I will understand that with time, but I would like to ask
Yes,
right
yes.
now is that how many dimensions there can be for maybe one type of problem or one type of space, like
What is the dimension now? You know what dimension? How
yeah,
dimension is defined now? So mathematically,
yeah, and
dimension is
maybe
defined number of these vectors in the basis. So now if you see why is this called as 2D? Because you just require two dimensions, you just require two vectors. These are the basis vectors. Basically, cardinality of basis is called the dimension mathematically. Again, we'll come up with these concepts and everything will make sense. Everything will start making sense. So why is this called R2? Why is it called two dimension? Because we just require two matrix, this I and J, we require two vectors, okay, to represent every point on this plane. That's why they are called as 2D. Okay, in 3D we require three basis vectors. Okay, what are bases? So basis vector is basically a set of vectors, and the cardinality of that set is called dimension. Okay, what is dimension mathematically? Cardinality of basis. So base, this is a set. So the basis, let's suppose this is a basis set. So we have a set which will act as basis, and and then the number of vectors in those in the basis set is called as the cardinality. So here we require just I and j as the basis for our vector space, because this is enough to represent every point that's there on the space. So we'll call this R2. Okay. Not again, I am not satisfied with my answer, because it requires a lot of understanding of what basis is, what is span, what is dependence, linear independence. I don't want to go so mathy. So right now I just want to touch the basics, but I hope that at least you got the notion what I'm speaking about. What is the meaning of dimension? So high level, we spoke two things about dimension. It depends on the questionnaire. If you are saying what is the size of the image, okay, tell me the size of the image, I'll say this is a 2D. If you ask me in the information that is in the, I'll say it is ND. Okay, because we require ND, and then we'll slowly and slowly abstract out our way, and we'll go into the mathematical details of what bases are, what these what basically this span is, what is an independence, what is dependence, and stuff like that. But I hope at this point these answers were probably the answers that I gave. It should no, you should not able to understand these. If you are able to, there is a problem then, because then I don't need to teach you linear algebra. And if you are not able to understand, good, because you are in the right class then. Were you able to understand 100% of these answers? You should not. If you
I'm more confused now.
if you understood them 100%, then there are two things: either I teach really nice and I'm good at convincing, and the second part is that you already know these things. Then
No, I don't know. I really. And also, I would like to know whether there is any limit on the diamond on the basis that
no, but we'll
we
come
have
to
to.
these. These questions will dig them deeper, because otherwise the whole conversation go
Okay,
on
please.
on these basis.
Okay,
Okay,
okay, please go ahead.
so that's
Thank you very much.
that's why usually I don't take questions. I take them at the end. Everyone with me? So who is sleeping? Who does not raise the hand, I'll consider them sleeping. I just saw some people raising their hand. That means most are sleeping, huh? Yes, yes, yes. Are you listening? At least give me some
Yes,
signal that. So now basically what I said is, so we use two systems of measuring that position of a point. So in both the systems, the D came out to be like this. So if we had a point P which belonged to n-dimensional space, and we'll see what dimension means. So take just a leap of faith that whatever I say dimension is, take them as like this, the numbers that I require to represent it. Okay, basically the number of numbers, that I do. Here I have x1, x2 till xn. So I'll call this an n-dimensional point or n-dimensional vector. So for that, if I have to compute distance of this point from the origin, so what I'll do is I'll just say summation of xi whole square, I goes from 1 to n. This is the distance. Now what we are going to do, because now what I said is we have to do certain tasks. We just computed now the distance of the point from the origin in coordinate system, and we also can see it visually, and we can do a lot of stuff on this 1D, 2D, 3D, whatever we can see, and we can just visualize them. But beyond 3D we cannot visualize. So it is better to have these formulations. Okay, and you should not memorize the formulations also. So after that, what we are going to do is now we are going to see what is the distance of the point within themselves. Now if we have two points, so we have point P1 over here, we have point P2 over here. Okay, now I need to compute the distance these points have. I need to compute this distance. Okay, so now the heading is a distance between 2 points. Now you understood the point, you understood Cartesian plane. Now you know that this point can be x1, y1, and this point can be x2, y2, something like this. Okay, now we have to understand that how to compute this distance. Okay, how to compute this distance. So again, we can show a mathematical proof how to do that. So you should be able to answer. Let's suppose we'll do one thing. So how we can prove this? Okay, we can make a right angle triangle some way, and let's suppose this is this is one vector that we have. This is my P2 vector, and this is my P1 vector. Okay, now somehow I need to compute the right angle triangle, and after that what I can do is, if I have the right angle triangle, and then I can use the Pythagoras theorem, and after having Pythagoras I should be coming up with the formula. Okay, so now what should I do is I should and this is not right angle every time, so this P2 can be here also, so this P2 can be here also. So if I draw this, so this cannot be right angle, so I should be able to form a right angle triangle such that, so whenever I basically draw these points, I should be able that should be a right triangle. It should not be that I'll just, let's suppose this is my right triangle, I'll use the formula. No, my P2 point can be here also. This P2 can be sometimes here. So then I have to compute this distance. And you can clearly see that if I join these two lines, this is not right angle. This is not right angle over here. So that's what I'm saying. We have to make a right angle triangle such that when we make this right angle triangle, that time what should happen is, so I should be able to then use Pythagoras theorem to come up with the distance formula. Okay, so distance between these points. Okay, now let's go to that proof. So how to do that? Let me come up with this point P2 again here. So this is my point P2. This is my point P2, and this is the distance I'm interested in, and this is the distance I'm interested in. Okay, so what I can do is, if I somehow, let's suppose I have this is x2 and x2, and this is my y2 point. Okay, so what I should be able to do is, I should be able to come up with some right angle triangle. Let's suppose I define a point, some point x2. Let's suppose I have some point which I have x2, and I should be having y1. Let's call this. Okay, because my goal is to come up with a formulation which should be so generic, and I am doing it right in front of you, and even I don't know the solution. That's the thing. My mind, I told you my method. My method of thinking is like this. My method is, I should come up with a right angle triangle. I should come up with the right angle triangle. And I told you the point is that I should not come with the right angle triangle which is just perfect to this example. The question should be, I should come with the right angle triangle where if I draw that point should always make this triangle a right angle triangle. Okay, that's my goal. That's how I should see it. Okay, and somehow I should, and the side should be this. This should be the side. So what I can do is, if I somehow draw this point, let's suppose I have this point over here. Okay, if I drop this point, let's suppose I'm just making the random guesses. So if I drop one point, so what will happen there? If I drop some other point, can I come up with a right angle triangle? And which I will basically then from that I can apply the Pythagoras theorem. See the thinking process. So here I'm not just here to memorize you. I'll tell you, okay, here this is why we can make right angle triangle, and then we can do this. So better is you should learn the thinking process. So learn the thinking process this way. So what I'm saying is, so you have these points x1, y1, you have the other points x2, y2. So I'm trying to find a point such that I can form a right angle triangle. Then I'll use Pythagoras theorem to come up with the formula. Okay, so how to do that now? So what I'm saying is, I'll come up with the point. Okay, now the coordinates of the point should be, so here this is my x2, and this is my x2, and this is my x1. I'll come up with the point C, which will have coordinates x2 and y1, which I wrote over here. Alright, this is where is my x2? This is my x2, and where is my y1? So y1 is somewhere here. Okay, this point over here. So if I have to come up with x2, so x2 is the point. This is here, and y1 is somewhat here. Okay, so I came up with this point. So this is the point. So this is the point over here. The coordinates of this is x2, y1. And now if you see, I can create a right angle triangle. This is one side and this is other side. Okay, and I had this as my hypotenuse. Now you see the method. Okay, the method was that I should come with a right angle triangle, and after that I'll use the Pythagoras theorem in order to find this distance. Let's have this distance g now. Now how I came up with this thing, I said I should be having this x2 and y1 because I want to include this side. So that's how I created this right angle triangle now. So now I'll be able to compute this distance, and I'll be able to compute this distance. So what's the distance of this? Because now it lies in y coordinate. So the point here, it is at y2. This is at y1. So this is y2 minus y1. So this distance over here. So because in order to reach here, I have to go till, let's suppose, y1, and in order to reach here, I have to go to y2. So y2 minus y1. So this is the distance of this point. Okay, and for this, what distance? Because it lies in x-axis. So this point is at x1, and this point is at x2. So I can say x2 minus x1. Okay, these are the numbers that represent how far are these points. Okay, what is the length of these points? Okay, now I can use Pythagoras theorem. This d square is equal to x2 minus x1 whole square plus y2 minus y1 whole square, and then d is equal to under root of this minus x1 whole square plus y2 minus y1 whole square. This is the logical reasoning part. Okay, so let's suppose you can now memorize this, but you won't be able to get through the method. So my notion was, okay, somehow I'll use Pythagoras theorem because I'll include this side. Now I said I'll come up with a point which will have coordinates x2 and y1, and for that what I'll do is, and then I'll make this right angle triangle, and I have the distance of this. I have distance of this side. Then I'll use Pythagoras theorem, and I came up with the distance. So if it is 1D, so 1D is easy case. Okay, if it is 1D, let's suppose, and if there are 2 points, so if this is 0 and this is my point 1, this is my point 2. So what I can see is, because they are just scalars, so I can say let's suppose this is represented by x1, this is by x2, I can say x2 minus x1. That is how I just do it in 1D. So in 2D, this is the way. In 3D, again the similar way. You can somehow construct these things. But now generic formula I can write. I said mathematics deals with it deals with the general cases. So if now I have a point in ND, if I have 2 points, P1 is in ND and its dimensions are x1, x2, x3 till let's suppose xn, and I have a point P2 whose coordinates are y1, y2 till yn. Okay, so now what's the distance? So distance will be under root of, okay, x1 minus y1 whole square plus x2 minus y2 whole square, and so on till xn minus yn whole square. So here d is equal to under root of, I can write in succinct format, summation of xi minus yi whole square. I goes from 1 to n. This is the distance formula between 2 points. How you can compute the distance between 2 points. So now for us these are vectors. Okay, for us these points are vectors. So basically what we are trying to do is we have vectors and we now learn to compute distance. So what we saw so far is how to compute distance of a vector from origin. And the second thing we learned is distance between two vectors. Between two vectors. This is what we saw so far. So for this, the formula is something d is equal to under root of, which is our origin, so xi whole square summation of I goes from 1 to n, and d here is equal, so I should write it with different color. So this d is equal to under root of summation of xi, I is equal to 1 to n. Now this is going too mechanical, but you know the basis, you know what is so what is the path that we took to reach here. So d over here is under root of xi minus yi whole square summation goes I from 1 to n. So here you can get confused at two things. So what you can say is, so sir was saying right here, so we are representing point by x1 and y1. So now suddenly he said the points are represented by x1, x2. I was getting out of numbers. If I said x1, y1, then I have to say z1, then I'll get out of numbers. So what I said is, I said I'll use x for one point and y for other point, and then I'll use these subscripts 1, 2, 3, 4, 5, and each of this basically is a number. Okay, x1, x2, x3, x4, x. It's not just along the x-axis. These are numbers. Okay, and they may be along different axes. And then this is p2. I chose this letter y to represent this point and 1 for the other number, 1, 2, and this is the subscript. That's why these formulas came out like this. This is the formula, and for this also I did the same. So when I was representing 1D point, I just used it x1, and for other 1D point, I said x2. So that's the similar thing I used here. So I said if I have a point in n dimensional, so I will represent thereby x1, x2, and xn. This is the representation of point in n dimensional, and I'll call these each thing is a number here. X1 is a number, x2 is a number, xn is a number. Okay, and I use that because I had to make choices. So the choice here was I had to choose a letter and I have to choose a representation. So what I said is I was using initially x1 and y1 for 2 points. Then when the dimension increased, I could have increased. I could say z1. Then again, if I increased it, I could have used some, let's say a1 now. So better than this, what I said is I said I'll represent points by this x1, x2, x3, and till xn. And this is my first point. This is my point 1. Okay, point second can be represented by some other number y1, y2 till yn. Okay, now if I have third point, I can use p, z1, z2, or maybe zn. So I can choose other representations also. So usually math gets tricky by the representations. Okay, that's why I'm clearing these points up. This is one type of representation. I can choose to do it like this. I can say p is equal to x11, x21, x31, and so on, xn1. So this is my superscript. This can represent my number. Okay, number of the point number. So this is point first. So if I have a second point, so I'll say x21, x22, x23, and so on till x2n. So this is my second point. This is my first point, the second point. Representations are different. Is it clear? Because sometimes, most of the times, this will happen. You understand a thing, but you won't understand notations. And notations will be something is crazy there. You are seeing these super subscripts, different letters here and there. Then you are saying, what is this? So usually what I say is, mathematics is like poetry. And poetry, for the poetry to understand, you should know the vocabulary. Okay? If you read poetry, let's suppose in Chinese, you won't be able to understand a thing. Why? Because you don't have the vocabulary. So in mathematics, this is just a succinct way of representation of the reality. But in order to know that reality, what you should know is, you should know the notations used. That's why good papers or good books, they have a full page dedicated to notations. They say that these are notations we use so that they don't create any unnecessary confusion. So here I said I on purpose did it so that I can clear this up. So I initially was using x1 and y1 to represent just single point, and then suddenly I use only x for one point, then y for other point, and suddenly I also change the representation. So takeaway from here is, okay, learn the notations before going to understand a paper or something. So if you are good with notations, you understand what this notation symbolize and what does this mean, it will be probably easy for you to understand more things. Okay, otherwise you will be going here and there with notations. So that I made the point clear over here. So I changed different notations, and I hope that if you watch this lecture probably once more, you should be able to understand what I was talking about. So I said mathematics is like poetry. In order to understand the poetry, you should have the vocabulary. You should necessary vocabulary to understand the poetry. Okay, necessary vocabulary, here's the notation. You should be able to know the notations and what do they represent and what do they symbolize, and after that you will be able to represent this. So now the formulation in our ND case was like this. So we saw now two things. So we saw distance. So distance, and this was from the origin, and the distance was from between points or between vectors. Okay, then we saw the case for 1D, 2D, 3D, and we generalized it to ND. This was the generic formula that I wrote was summation of, this is under root, summation of I goes from 1 to n, xi whole square. And for this I wrote under square x to, let's suppose, minus x1, or maybe xi minus yi whole square, summation I goes from 1 to n. Okay, this is the distance. Okay, for 1D 2D cases this is easy to write. Okay, it can come from here. So again, one more thing. So here you can get a confusion. So usually I am sometimes using y1 minus x1, sometimes I am using x1. Now you see this is squared, so it doesn't matter how I write it. I can write x1 minus y1, or I can write y1 minus x1. Why? Because I am squaring it after all. So if I write minus 2 whole square, if I write 2 whole square, that's the similar thing. That's what I did here. So I can just shuffle these things here. Okay, I hope at least till this point everything was clear. Any questions till here? So far we have defined, if I summarize this, we have defined what a point is, okay, and then we said what's the relation of this point with the vector from a computer science perspective, and we saw a lot of these things. And then we said if we have to measure distance between these points, because measuring distance becomes really important, and I'll show you tomorrow. So I'll basically, the concept that I want to teach you is called as principal component analysis. Okay, principal component analysis, where you do the dimensionality reduction. So what is that? We'll go to that. But for that, you basically need an understanding of these how to project. You need concept of projections, and for these projections you should know how to compute distances between the vectors. Okay, this PCA is a beautiful algorithm. This is a beautiful, well-grounded mathematical algorithm. Okay, and it is mainly used when you have high dimension data. You want to reduce that data. Okay, and for that you need these projections, and for those projections you need the distance. That's why I cover the distance between 2 points today. That was my thinking. Why should I cover the distance? And after this, once I know this, now I have vectors and I have many things. So now I'll see operations that are allowed on the vector spaces. The operations I can do on these vectors. I can probably add them, I can subtract them, I can multiply them, and there will be ways of multiplication. Okay, and all these operations we'll take tomorrow. And after I'm done with the operations, and we'll move on to how do we represent these lines, how do we represent shapes. Okay, why to do that? Because sometimes if you have doing a machine learning task where it's a classification, you have spam emails or you have no spam emails. They're called ham. So now if emails are like this, I can represent these emails by a bunch of numbers. Okay, if emails are like this, something like this. So if I can draw this line, okay, and on this side there is this no spam, and on this side there is spam. So I should be able to represent this line now mathematically. So I should be come up with this line. Okay, this is the line which separates these two. Okay, because I somehow represent emails by points. I said okay, email is represented by just two numbers. So here that numbers are there. That's where these vectors come in. So for operations, I need those cross product and everything. And after that, we'll learn about representation. How do we represent mathematically these lines, different shapes? These basically they're called as boundaries. So in mathematics, you usually call them probably conic sections or something. So in our machine learning terms, we call them boundaries. So you might have heard about linear decision boundary. They call them decision boundaries because this is the boundary which separates out these two classes. Usually we have task of classification if you want to classify things. Okay, so we must know mathematically how to represent these things. But it all boils down to to these basics. You must have really good grip. Please and please, if you have time, watch these lectures again and again so that these things become intuitive. And I'll try my level best to explain you the things with real world examples so that you get a better hold of these things. Okay, and next topic will be probably operations of these vectors, and then we'll be covering this, and we'll be more or less done with the basics. Okay, after that we'll directly take up linear algebra from solving the linear equations. That's the fundamental question of algebra. Okay, so with this I'll stop the recording here. Any questions, I would like to take them now.